Well, thank you very much. Thank you for the invitation. It's a pleasure to speak here. So I apologize in advance because I've been sick for 2 days actually. So I hope this won't be noticeable. Um, so this is a joint work with Mihailo Tsekic. It's something that we did actually two years ago, I think. So some of you might have heard some part of it actually. Okay. So how does this work? Okay. Okay, so I'm gonna start with something very classical. I'm pretty sure that all of you have heard like this 100 times, but it's a great motivation for what I'll be speaking about afterwards. So the starting point is the classical spectral inverse problem. Can one hear the shape of a drum? So this is the famous paper by Katz, 1966. So the problem is if you're given a Riemannian manifold, MG, so possibly with boundary with or without boundary. You want to know whether you can recover the metric G from the knowledge of the spectrum of the Laplacian of G. And of course, so this is the classical problem. Of course, there's always a gauge group acting, namely you can't expect to recover the metric G exactly, but it's only G up to isometries. So in other words, if you have a diffeomorphism on your manifold and you pull back your metric by your diffeomorphism, then you get a new metric, but they have the same spectrum. Okay, so this is the gauge. This is what we call the gauge group of the problem, and Katz question can be rephrased as can we recover the metric up to the action of this gauge group, basically. So in general, the answer is no. There are famous counterexamples to this problem in general. So the first counterexample was actually due to Milnor and was found even before the question was asked. So there are pairs of tori which are isospectral but not isometric. And then there's a paper by Vinieras who found pairs of hyperbolic surfaces, which are isospectral but not isometric. And then there is a lot more which is known about this. There's also a famous counterexample in the plane with a polygonal domain. So this is the paper by Gardner, Webb, and Welpert. But there are also positive answers to this problem. So there are positive answers if you consider one parameter family of metrics, which are isospectral. So these are the works by Guillemin and Kazjan and Crook and Sharafudinov. And more recently, much more recently, Hazar and Zeldich proved this rigidity of the spectrum for domains which are ellipses of small eccentricity. So it's a very narrow subset of the set of all domains in R2, but still it's a positive answer to this question. So that was a breakthrough. Okay, so this is the classical problem, but I'm going to be speaking about something slightly different. Namely, I'm going to be speaking about the spectral inverse problem for connections. So here, what we're going to do is we're going to fix the background metric G. So we're going to fix the topology of the manifold. It's going to be closed, namely compact without boundary manifold. And we're going to fix the Riemannian metric G on this manifold. Okay, and everything is assumed to be smooth. Now, on that manifold, I'm going to consider E a Hermitian or Euclidean vector bundle over my space. And I'm going to equip this vector bundle with a connection that I will denote by nabla E. And I assume that nabla E is unitary. So if you've never seen connections in your life, I'm not going to give the definition of connections, but basically the only thing that you need to know to be able to follow my talk is what a connection does for you. And the main thing that a connection does for you is parallel transport. Okay. So namely, if you take 2 points, x minus and x plus on your manifold, you take a path gamma connecting x minus and x plus. So there's the fiber of your vector bundle above x minus. You can pick a vector here, vector xi in ex minus, and a connection allows you to do the parallel transport of xi along this path gamma and with respect to this particular connection that you've chosen. And that gives you a new vector here in ex plus that we called tau gamma of xi. Okay, so you see that there's a map that appears here, which is tau gamma. It's a linear map from ex minus to ex plus. and it's the parallel transport of your vectors along the path gamma. And the fact that the connection is unitary implies that the map here is an isometry. Okay, so there's a metric on each fibers of your vector bundle, and this map tau gamma, this parallel transport, preserves this metric. Okay. Okay, so we have a manifold, a vector bundle, a connection on this vector bundle, and now we can define the connection, or it's also called the Buchner Laplacian associated to the connection. So what we do is, well, we just compose nabla e with its adjoint. Okay, so nabla e star nabla e. That's what we denote by delta of e. Okay, and that's a Laplace type operator. So it's an operator, it's an elliptic operator of order 2 that acts on sections of the bundle E. Okay. Um, so it's an elliptic operator of order 2. It's non-negative, so it has a discrete spectrum. Okay, that's the very classical theory. And the question that I want to ask is, a very similar question to that of Katz, namely, does the spectrum of the Laplacian determine the the connection first and the vector bundle as well up to gauge? Okay, so up to gauge here, if you're familiar with with the isospectral problem for metrics, the gauge group here is what will replace the group of diffeomorphisms, basically. Okay, so I'm going to describe this gauge group in a minute. And here it's really the same problem. So we want to recover the pair E and nabla E from the knowledge of the spectrum of the Laplacian. Okay, so there are two things to recover there. That's what you should remember. First, the connection itself, and second, the topology of the vector bundle. Okay, so what is the gauge group in this problem? So it's something that is sort of analogous to the group of diffeomorphisms in the case of metrics. So here, what plays the role of isometries are fiber-wise isometries. So namely, it's the set of all sections P. So there are sections defined over M with values in isometries of E. So namely, at each point X in M, P of X is an isometry of your it's a linear isometry of your vector bundle. Okay, and this is the gauge group of the problem. Namely, if you have a connection nabla E, you can pull it back by this map P. So you can consider P star nabla E. So it's defined by conjugating your connection by P, and you can check that this defines a new connection. And these two connections are said to be gauge equivalent, but they really have the same intrinsic data. Like if you compute the spectrum of the Laplacian, for instance, you're going to get the same eigenvalues. If you compute the holonomy, the holonomy of the two connections, they're going to be conjugate. So the trace of the holonomy will be the same, etc. So like all the intrinsic data you can think of are all the same. Okay, just like for metrics. So this is the gauge group of this problem here. Okay, and so here's the theorem that I'm going to try to prove in this talk. So this is a theorem that we proved with Mihailo Tsekic. Okay, so we fix an integer n greater or equal than 1, and the theorem says that there exists an integer q of n, which I will describe in a minute. Such that, so if we consider we fix a Riemannian manifold of dimension n plus 1, which has negative sectional curvature and simple length spectrum. So I will explain what this means in a minute. Then, if I look at the spectrum map, so it's the map that takes a pair, a vector bundle, and a connection, and associates this the spectrum of this pair. Okay, and I have to restrict to vector bundles of rank less than q of n. This is where this number appears. Then the spectrum map is injective. Okay, so in other words, if you have two connections on a vector bundle of rank less than q of n, and they have the same spectrum for the connection Laplacian, then these connections are gauge equivalent. Okay, and what the theorem says is also that you can a priori assume that the two vector bundles you start with are actually different. And this theorem tells you that no, they're not different. They're actually the same. They're the same vector bundles. Okay. So when I say injective here, it's always injective up to gauge. Okay, so I'm not going to repeat these. So what is this integer q of n? I'm not going to define it right now, but it's an integer that is defined via real algebraic geometry. So that's a surprise. It's quite unexpected actually here in this problem. It's not a number that we can effectively compute. I mean, it's still unknown unless for some very small values of n, basically. But if n is a power of two, it's known. So q of n when n is a power of two is n basically. And there's a bound of you can bound q of n between n and n over two. Okay, but the general value is unknown. Okay. Sorry, what am I doing here? Sorry. Okay, sorry. Okay, so what we're going to do is what I'm going to show is actually that this theorem about the spectral inverse problem for a connection is a consequence, is a corollary of a more general result obtained for another problem, which I will call the Holonomy inverse problem. Okay, so let me now try to explain what this problem is about. So the standing assumption will be that we have a Riemannian space of negative sectional curvature. Okay, we can actually assume that we can relax this assumption and only assume that the metric has another geodesic flow. Okay, if you've never seen this assumption, it doesn't matter. You can just assume that the metric has negative curvature. But what I'll be saying actually can be generalized to this more general context. Okay, so we have this fixed background space of negative sectional curvature, and I will denote by C the set of free homotopy classes on my space. Okay, so then there's a lemma. It's a very classical fact that says that for every free homotopy class, there is a unique closed geodesic in this class, and of course, this unique closed geodesic depends on your metric. Okay. So the class is C. So here, for instance, I depicted a genus 2 surface, and C is the class of curves that wind once around the central, the central neck of the surface. So this is your free homotopy class. And the lemma says that there is a unique closed geodesic in this class. So the geodesic is here in blue, gamma G of C. And it's actually the curve that minimizes the length among all the curves in this free homotopy class. Okay, so that's a fairly standard lemma in Riemannian geometry. And okay, so now we're going to fix a free homotopy class C. We have this closed geodesic gamma G of C. And now what we can do is, well, we can consider the parallel transport on our vector bundle with respect to our unitary connection along this curve gamma G. Okay, so what we can do is we fix a point X. It's an arbitrary point. The quantity that I'm going to define doesn't depend on the choice of point. So we fix a point X on this curve gamma G. Okay, then we have the fiber of the vector bundle above X. So this is the vector space EX here. We choose an arbitrary vector xi here. And what we can do is we can parallel transport xi along the loop gamma G of C. And then we come back exactly at the same point because it's a periodic orbit. So by assumption, by definition, you come back exactly at the same point. And you get a new vector, which is tau gamma of xi. Okay, and you see that you get a map, tau gamma, which is a map from EX to EX. It's an isometry. And it's the parallel transport along gamma. Okay. And so we can define an operator which is called the geodesic Wilson loop operator, and which associate to a pair E nabla E the trace of all. The trace of all these maps tau gamma. Okay, so to a pair E nabla E, I associate a sequence indexed by free homotopy classes such that what is the value of this sequence at a specific free homotopy class? Well, it's the trace of the parallel transport along the unique closed geodesic in this class. Okay, so this is what we call the geodesic Wilson loop operator. In the physics literature, it's known as the Wilson loop operator when you take the trace of a connection along a path like that, and we call it the geodesic Wilson loop operator because we only consider curves which are geodesics actually, which are closed geodesics in this case. And the remark is that this only depends on gamma g of c, namely does not depend on the choice of point on your geodesic, okay, because you take the trace actually. So this is the reason why it doesn't depend on x. And, sorry, it only depends on the gauge class of the connection. So if you take another connection in the same gauge class, okay, namely it means that you just pull back your initial connection by this isometry p that I introduced 2 slides ago, then you get the same number. Okay, so this geodesic Wilson loop operator is really a well-defined operator on the space of all connections modulo the gauge group of connections. Okay. If you're familiar with a Markland spectrum, for instance, it's exactly the same. The Markland spectrum is the length of all closed geodesics marked by the free homotopy of the manifold. And there's also a gauge group here, which is the group of diffeomorphisms on your manifold. And this Markland spectrum is invariant by the action of this gauge group. So here it's exactly the same, except that we work with connections and the gauge group is slightly different. Okay, and so the Holonomy inverse problem is, well, is this map W injective? Namely, if you have two connections and the trace of their holonomy is the same along every closed geodesic, then can you prove that the connections are not exactly the same, but the same up to this element of the gauge group? Okay, so it's injectivity modulo this gauge group. Yeah, so that's what I wrote here. So you take two connections, nabla E1, nabla E2, and you assume that for every closed geodesic, the trace of the holonomy of the first connection is equal to the trace of the holonomy of the second connection. Then can you prove that E1 and E2 are actually the same vector bundles and the two connections are gauge equivalent? And the answer is, so we're actually able to answer positively to this question in some particular cases. So the assumption is that, so it's the same standing assumption, the background space, the Riemannian manifold has negative sectional curvature, dimension n+1. And what we can prove is that if you look at this geodesic Wilson loop operator on the space of real vector bundles of rank less than cube n, equipped with unitary connections, then this Wilson loop operator is injective on this space. Okay, so we can indeed recover the topology of the vector bundle and the connection up to gauge here. But of course, this is under the assumption that the rank of the vector bundle is less than this very mysterious number cube n. Okay, and yeah, so I stated the theorem for real vector bundles, but we actually have a similar result for complex vector bundle. Okay, so yeah, so I'm going to try to explain what this number cube n is, but before I do that, let me just state this conjecture. So what we actually conjecture is that this geodesic Wilson loop operator should always be injective on odd-dimensional negatively curved manifolds. So why is it so? Because the Wilson loop operator is actually never injective on even dimensional manifolds. So there's an easy counterexample provided by self-dual and anti-self-dual forms on even dimensional manifolds, but that doesn't exist. That doesn't show up on odd dimensional manifolds. There's also, and here this counterexample is not a contradiction, because here in my previous statement, I had no assumption on the parity of n. Okay, n+1 here can be even or odd, it doesn't matter. Here, there's no contradiction because this counterexample provided by self-dual and anti-self-dual forms is, well, the bundles have a very, very high rank, which is like n to some power, very large power. And this is bigger than Q of n. So there's no contradiction here. Let me also mention that there are actually earlier works related to this, and more specifically, Gabriel Patronin, who is in the audience, I think. Yes, he is. Hey, Gabriel. So he studied the case of the one dimension, sorry, the rank one case, namely the case of line bundles. So he was interested in something which is called transparent connection, but this is intimately related to this, and he proved injectivity for a line bundle. So in the case where the rank of the bundle is one. Okay. Okay, no, sorry. So before explaining what this number Q of n is, let me show you how theorem A implies theorem B. Okay, that's a very quick computation, actually. So my claim is that theorem A, no, sorry, theorem B implies theorem A. Okay, okay, this is wrong. Theorem B implies theorem A. So in other words, the Holonomy inverse problem implies the spectral inverse problem for connections. Okay, so why is it so? Well, because if you take two connections, nabla E1 and nabla E2, with the same spectrum for their connection Laplacian, then what you can do is you can apply the Dirichlet-Guillemin trace formula. So it's a formula that relates on the left-hand side the spectrum of this operator. So on the left-hand side, on the spectral side, um, you compute the trace of e to the minus I square root of the Laplacian t. Okay, so on the left-hand side, you get a distribution in t, which is the sum over j of e to the minus I square root of the eigenvalue times t. Okay, and the trace formula tells you that this is equal to a sum running over all closed geodesics of something, which is, so it's the length of the geodesic times the trace of the holonomy of the connection along this geodesic. So this is where it shows up, times the Dirac mass, okay, divided by the Poincaré, well, the square root of the Poincaré determinant of the map. Okay, so that doesn't really matter. So it's not an exact formula. There's a remainder, but the remainder is an L1 lock function. So if you assume that your Riemannian space has simple length spectrum, it really means that you can recover this number circled in red from the knowledge of the spectrum on the left-hand side. Okay, so if I give you the eigenvalues on the left-hand side, then you are able to recover this number circled in red. Okay, in other words, the trace of the holonomy of the connection along every closed geodesic. But that's by definition, this is the geodesic Wilson loop operator. So in other words, if the two connections have the same spectrum for their connection Laplacian, then they have the same, well, the Wilson loop operator evaluated on these two connections is the same, give you the same numbers. And so if you can solve the Holonomy inverse problem, then, well, it implies that the two connections are gauge equivalent. So it solves the problem. Okay. So basically theorem A boils down to proving theorem B, namely the injectivity of the Wilson loop operator. Okay. Okay. So here is the strategy of proof for theorem B, for the Holonomy inverse problem. So the key ingredient basically is something called the non-abelian Lifshitz theory, which is something that we developed with Mihailo Tsekic. And it's something that heavily relies on the hyperbolic structure of the geodesic flow. And then the end of the argument is based on Fourier analysis in the unit tangent bundle. And it's something that I'm pretty sure that most of you are familiar with. It's related to tensor tomography, injectivity of the X-ray transforms, and stuff like that. So there's yeah, and there are things like Pestov identities, for instance, which show up. And the end of the argument is where the real algebraic geometry appears, and where this number q, this mysterious number q then appears, and it's related to the classification of polynomial maps between spheres. Okay. Okay, so let me try to explain the proof of this theorem. But maybe first, I said that I was going to define this number q of n. Okay, so here it is. Okay, so before delving into the proof, let me try to introduce this number q of n. So for that, I need to talk about polynomial maps between spheres. For me, the sphere is the round sphere in Rn plus 1. Okay, so the sphere Sn is the set of all points in Rn plus 1 with norm equal to 1. Okay. So we're going to be considering maps from Sn to Sr, where n and r are, well, they may be different integers. And we say that this map is a polynomial map if when you write f in coordinates, so it has r plus 1 coordinates, and all the coordinate maps are all the coordinate functions are polynomial with respect to the variable x. Okay. So f of x should be p0 of x. This p0 should be a polynomial of x. It's to pr of x, and pr of x should be a polynomial in x as well. Okay. Sorry, what is that? So the fact that f maps the sphere to the sphere is easy to translate into a condition on these polynomials, namely when you compute f of x squared, you should get, well, you should get 1 for every x with norm 1, basically. And this is equal to the sum of the pi squared. Okay, so you see that you get a sort of, this is where it's very algebraic in some sense. You get a sum of polynomials such that, you get a sequence of polynomials such that when you sum, when you sum them, well, when you sum the squares, you get 1, the constant function 1. So it's very algebraic. So there are famous examples that do this. For instance, the Hopf fibration. It's a map from the sphere S3 to S2. It's defined, so it's completely explicit. It's defined in the following way. So if Z0 and Z1 are two complex numbers, so this is a point in C2, which you can identify with R4. This map has an explicit expression. So it's Z0, modulus of Z0 squared minus modulus of Z1 squared, comma 2 times Z0, Z1 bar, okay? And you can check that this is indeed a map from S3 to S2. Namely, what you have to check is that if you compute the norm, the square of the norm of f, then you should get 1 whenever Z0, Z1 belongs to the sphere S3. Okay, so that's an easy computation. So that provides an example of a map, an algebraic map, which is non-constant, which goes from S3 to S2. And then you may wonder, well, is there such a map from S3 to S1? And the answer is actually no, there's no such map. So what we're going to do now is more generally, if n is the dimension of the sphere we start with, we're going to define q of n as the least integer for which there exists a non-constant polynomial map from Sn to Sr. So in other words, here for n equals 3, q of 3 equals 2, because there is a map from S3 to S2, but there's no map from S3 to S1. Well, the only map from S3 to S1 is the constant map, basically. Okay, so this is how q of n is defined. And the theorem, there's a theorem by Wood. It's an old theorem, 50 years ago. So Wood proved that if there's a power of 2 between r plus 1 and n, then there is no non-constant polynomial map between Sn and Sr. Okay. So here you should notice that r is always less than n, basically because, for instance, if r equals n, it's easy to find a map from Sn to Sn. You just take the identity map, basically. Okay. So the consequence of this theorem is that q of a power of 2 is equal to the power of 2. And consequently, q of n is bounded between n over 2 and n. Okay, so that's easy to check. And you can actually start computing the first values of n. It's not very difficult. In particular, there are other Hopf fibrations, and they're very useful for that. So using them, you can compute the first values up to q of 15. And then you can sort of keep playing this game, and there is a more general construction, which is also due to Hopf, which allows you to construct more and more maps like that. But this construction stops working at n equals 48. So the first unknown value is q of 48. Okay, this is, and nobody knows, basically. It amounts to finding a polynomial map between S48 and S47, but this is unknown. Okay, So this is, well, we have defined the number q of n now, and now let me try to sort of to explain the main ingredients in the proof. Okay, so the proof heavily relies on the fact that the geodesic flow is a hyperbolic flow in negative curvature. So the background space is always fixed. It has negative curvature. Sm will be the unit tangent bundle for me, and phi t will be the geodesic flow. Okay, so if you take a point x, direction v, then you can follow the geodesic, the unique geodesic determined by x and v, and that defines for you geodesic flow on the unit tangent bundle of your space. Okay, and it turns out that in negative curvature, this flow has a very strong, it's uniformly hyperbolic. Okay, so there's a flow direction, but then orthogonally to the flow direction, uh, the flow either contracts exponentially fast or expands exponentially fast. Okay, so this is what is written here. And in particular, a consequence of that is that periodic orbits are dense and they actually equidistribute in the unit tangent bundle. Okay, so that will play an important role for us. Okay, so now, well, not only do I have a metric with negative curvature, but I have a vector bundle over my space equipped with a unitary connection. Okay, so what I can do is if I start with a point x and a direction v, I can shoot the geodesic generated by x and v. Okay, and I can look at the parallel transport of vectors of E along this geodesic. And of course, I do that with respect to my fixed connection nabla E. Okay, so in other words, I start at the point x, direction v, I pick a vector xi here in the fiber above x, and then I do the parallel transport of xi, along this geodesic. Okay, and that gives me a new vector which sits above this point, and I denote this vector by c of xv. Xv is my point in initial direction, and then time t, because I do this for time t. Okay, so c of x, v, and t is what is called a cocycle over the geodesic flow. Okay, so here it gives you a map from cxvt is a map from ex. Okay, it's an isometry from ex, the fiber above x, to the fiber above this new point. Okay, this point, which is here, it's the projection of phi t of xv. Okay. And what is the Wilson loop operator? Well, it's just the trace of this cocycle along periodic orbits, basically. So if this is a periodic orbit for the geodesic flow, you pick an arbitrary point x, a direction v, which generates this periodic orbit, and then you look at this cocycle at x and v, and in time, L of gamma, where L of gamma is the length of this closed orbit, okay? And if you take the trace of this cocycle, well, this is going to give you exactly, the trace of the holonomy of your connection along the geodesic. And that's, by definition, that's the Wilson loop operator. Okay. Okay. So now what we're going to do is, well, we're trying to prove the injectivity of the Wilson loop operator. So we suppose that we have two vector bundles, two connections, and they have the same they have the trace of their holonomy is the same along every closed geodesic. Okay, this is the first equality. So in other words, the trace of these cocycles are the same along every closed geodesic. Okay, so this means that this is what I wrote here. It means that if you take k equal 1 here, it means that the trace of the holonomy is the same for the two connections. But of course, you can do this for for a geodesic, but you can actually do this for iterates of this geodesic. Like you can go twice around the geodesic, 3 times, and so on. And when you do that, well, you get iterates of the parallel transport maps. Okay, and all these iterates have the same trace as well. So this is the equality you end up with. The trace of all the powers of the holonomy of the first geodesic along this loop is the same as the trace of all the powers of the holonomy of the second connection along the same loop. Okay, so in other words, well, it's then it's a standard fact in algebra. You have two linear maps, A and B, say, and the trace of all their powers are the same. And so it's a trivial exercise to check that it actually implies that the two maps are conjugate. Okay, A is conjugate to B. So here, this is going to imply that the parallel transport along this loop with respect to the first connection, so tau nabla E1, will be conjugate to the parallel transport along the same loop, but with respect to the second connection, tau nabla E2. Okay, so there's an isometry from E1 to E2, P of gamma, that conjugates these two parallel transports. Okay. So here, this is the equality that I wrote here. Tau nabla E1 is equal to P gamma inverse tau nabla E2 composed with P gamma. Okay. Now the problem here is that you can do that for every single closed geodesic. Okay, and you get a map, an isometry P gamma for every closed geodesic. But the problem is that this is not clear at all that you can sort of glue all the maps P gammas that you get all together. Okay, because they may widely depend on the closed geodesic that you pick, and closed geodesics are dense in your unitangent bundle. So the non-trivial part here is to show that this does not happen, that there is indeed a globally defined map P that does the conjugacy for you. Okay, so this is the content of the non-abelian Lifshitz theorem that we proved with Mihailo Tsekic a couple of years ago. So if you take two connections that have the same trace along every closed geodesic, then there's a globally defined map P, which is actually an isometry from E1 to E2, that conjugates the two parallel transport maps. So we say that the two cocycles are cohomologous. So in other words, if you do the parallel transport with respect to the first connection, it's like applying P doing the parallel transport with respect to the second connection and then coming back by P. Okay. So this is what I did, what I tried to depict here on this picture. So in blue, you have the first vector bundle, E1. So you take a point X, direction V, you shoot the geodesic, you do the parallel transport with respect to your first connection. Okay, so this is what you have in blue. And what this theorem tells you is that this is the same as applying the map P, this isometry, so this gives you a new vector, P of xi, and then you do the parallel transport of P of xi with respect to the second connection. Okay, you end up there. And then you apply P inverse again, and this gives you exactly the same vector. Okay, so there is a commuting diagram here. Okay, and in dynamical systems, we say that these two cocycles over the geodesic flow are cohomologous when there's such a map P exists. Okay. It turns out that this equation here, this cocycle equation, so this equation that tells you that really the two cocycles are the same, you can actually rewrite it if you differentiate it with respect to t and you evaluate at t equals 0. You can rewrite it in a very neat and concise way. You can say that x of p is actually equal to 0, where x, this sort of, it's supposed to be a bold x, but it's yeah, okay, so in LaTeX it would be a bold x. This bold x is a differential operator of order 1, and you can think of it as a sort of lead derivative in the direction of the geodesic flow. Okay, what's sort of complicated is that this is a differential operator that acts on sections of a complicated bundle, which is the bundle of homomorphisms from E1 to E2. Okay, but these two equations, my claim, I'm not going to prove it because it's a bit tedious, but my claim is that the equation star here, this equation that tells you that the two cocycles are cohomologous, is really equivalent to this equation xp equals 0. Okay.
Is the bold x like a connection with a connection in the direction x?
Yeah, exactly. So what you do is there's a connection on the base M, you pull it back to the unitangent bundle, and then you plug in the geodesic direction, the geodesic spray in your connection. And this is bold X.
And that connection is somehow determined by.
Yeah, it's the induced. So there's a connection in E1, there's a connection in E2, And then there's a general thing that tells you that it induces a connection on the homomorphism bundle between E1 and E2.
And so are you here using like the difference of the two connections?
It's not the difference of the two connections. It would be more like a product basically, because the homomorphisms from E1 to E2 is equal to E2 tensor product E1 star. Okay.
Mm-hmm.
So when you have a connection on E1, you also get naturally a connection on E1 star. And then when you have a connection on two vector bundles, you can take the tensor product of the connection, basically. And this is exactly what I'm doing here.
I see. Okay. Thank you.
Um, but okay, so we have so to sum up, we started with two connections that have the same trace along every closed geodesic. And what we end up with, applying this non-abelian Lefeuvre theorem, we end up with a map P, which is defined on the unit tangent bundle, and it's an isometry between E1 and E2. Okay, so for every x and v, it gives you an isometry between your two vector bundles. And not only that, but also this map is invariant in some natural sense by the geodesic flow itself. Okay, so this is what we end up with. Okay, so then to conclude, I mean to end the proof, I need to do some Fourier analysis on the unit tangent bundle. So here I'm going to take advantage of the fact that the unit tangent bundle of my space is a sphere bundle over M. So in other words, for every point x0 in M, the fiber of the unit tangent bundle above x0 is a round sphere, which is naturally isometric to Sn, because remember that the base manifold has dimension n plus 1. So the round sphere has dimension n. Okay. What's very convenient is that if you give me a function now on the unit tangent bundle, then you can decompose your function in spherical harmonics in every sphere of this fiber bundle. So in other words, you freeze the base point x, you get a function on the sphere, and then you just decompose your function in spherical harmonics. Okay. So this is what I wrote here. If you give me a function f, I can decompose f as a sum of fk's, where fk is a spherical harmonic in every fiber of this fiber bundle. Namely, it satisfies the equation Laplacian on the sphere applied to fk equals k times n plus k minus 1 fk. Okay, so this Laplacian is called the vertical Laplacian. And we're going to say that f has finite Fourier content if the sum here is finite. So in other words, you only get a finite number of spherical harmonics in the decomposition. Okay, so there's a uniform number, capital N, over M, such that if you decompose your function in every sphere, there's a maximal spherical harmonic. Okay. And yeah, if you're familiar with tensor tomography, it actually means that so f has finite Fourier content if and only if f is the pullback in some natural sense of a symmetric tensor on the base. Okay, so I'm not gonna be using this, but. Okay, so what's quite remarkable is that this works for functions, but you can actually also do it for sections of a vector bundle. So this time, instead of taking a function on Sm, I'm going to take a section with values in this complicated vector bundle. You can actually forget about this. You just replace this by another letter like E, or it doesn't really matter that this vector bundle has this particular form. So what's remarkable is that you can still do it for sections of a vector bundle. So in other words, for the section F can be decomposed as a sum of, well, spherical harmonics or twisted spherical harmonics, namely a sum of FKs where each FK satisfies the same eigenvalue equation on each sphere. Okay, and here this is also the vertical Laplacian. This function fk belongs to the space omega k, and I define the space omega k to be the set of all sections such that if you're restricted to a sphere, you get a spherical harmonic of degree k. Okay, this is the space omega k. Now, it turns out that the operator x acts very nicely on this decomposition. Namely, if you take a section in omega k and you apply this differential operator bold x, then what you get is not something arbitrary. You get a sum of something of degree k minus 1 plus something of degree k plus 1. And this is a sort of far-fetched generalization of something that was already noticed by Guillemin and Kazhdan for the geodesic flow on surfaces, actually. But this still holds in this for sections of a vector bundle. So that's quite remarkable. So this is the first ingredient. The second ingredient, I'm not going to detail this identity, but there's an energy identity on the unitangent bundle that relates. It's called the twisted Pestov identity. So it is due to Guillermo, Paternin, Salo, and Ullmann in this form. And it's a very important identity that relates many important quantities in this problem. So I'm not going to detail this identity, but I just want you to know that the main consequence of this identity and the fact that X acts nicely on this decomposition is the following key lemma here. So the lemma says the following. It says that if you have a section which is invariant by X, so it's in the kernel of bold X, then this section has finite Fourier content. Namely, if you decompose it in spherical harmonics in every fiber, you only get a finite number of them. You only get a finite number of spherical harmonics. So there's a uniform over the whole manifold, a uniform number n, such that f is a sum of spherical harmonics up to degree n. Okay, and that's really a consequence of this twisted Pestov identity. Because here, basically, if you plug in xf equals 0 in the Pestov identity, you see that there are many simplifications. This term, the third term on the left-hand side, goes away. This term goes away as well. So you're left with this, and this is equal to something which, you're in negative curvature. So basically, the right-hand side has the wrong sign, and this is, the rough idea. This is how you get a contradiction, basically. Okay. So why is it useful for us? Well, we're going to apply this with, the section P, which is provided by the non-abelian-Lifshitz theorem. So remember, this was the section that was telling us that the two cocycles were cohomologous. Okay, so this section by this identity star was in the kernel of the bold X operator. So in other words, if we apply this to P, we get that P has finite Fourier content. Okay, so that will be very important for us. Okay, so this is where the polynomial maps between spheres come into play. So remember that this map P, it's a section defined on the unitangent bundle, and it's an isometry at every x and v. It gives you an isometry between E1 and E2. Okay, and by the previous by the Pestov identity, we know that this P has finite Fourier content. Now, what we're going to do is, well, we're going to freeze a base point x0 and m on the manifold. And we're going to look at the restriction of this map P to the round sphere above x0, okay? So this is the map that I wrote here. We look at the map that takes a vector v in the sphere above x0 and maps it to px0, v, okay? So v belongs to the sphere Sn, and px0v is an isometry from E1 at the point x0 to E2 at the point x0, okay? But these are, the point x0 is fixed. So E1 and E2 at this particular point x0, they're just copies of the Euclidean space, like R to the R, basically, okay? So in other words, this Px0v, this isometry, is just an element of the linear group SOR. It's just a matrix, basically, okay? So you see that we get a map from Sn to SOR that maps V to Px0v, which is, well, it's just a matrix, okay? It's just a matrix, so it has coefficients. And all the coefficients of this matrix have finite Fourier content. Okay, if I expand them in spherical harmonics, I should only get a finite number of spherical harmonics. But now you probably know that spherical harmonics on the sphere are restrictions of homogeneous polynomials in Rn. Okay, so in other words, you can rephrase this by saying that you have a map from the sphere to SOR. So it's a matrix, basically. It's a map from the sphere to the space of metrics. all of whose coefficients are polynomial in V, okay? And in particular, so now I'm trying to find a map from a sphere to a sphere. In particular, you see that if you look at a column, this is a matrix in SOR. So if I pick the first column, for instance, well, this gives me this gives me an element of the sphere SR minus one. So if this allows me to cook up a map from the sphere to the sphere Sn to SR minus one by just taking the first column, for instance, all of whose entries are polynomial. Okay, so I get a polynomial map from Sn to Sr minus one. But by assumption, since the rank of my vector bundle is low, it implies automatically that this map is constant, actually. This polynomial map is constant, namely, it does not depend on V. It's independent of the vector V. So in other words, this section P of xv, which initially depended on V in a sort of in a way that I could not control, basically, turns out to be independent of the velocity variable V. So in other words, it's really a section. It's really something that lives on the base manifold because it doesn't depend on the V variable in the fibers. So it's really a section. It's really something that descends to the base manifold M. Okay, so it's really a section defined on M with values in isometries between E1 and E2. And then it's easy to see that this invariance, this bold xp equals 0 equation, this invariance by the geodesic flow actually translates into this other equation. Okay, so P is scaled by a connection on this homomorphism bundle. But this is equivalent to the fact that the two connections are gauge equivalent. Okay, it's just a rephrasing of this condition. So we're done. We started with two connections that have the same trace such that the trace of their holonomy along every closed geodesic is the same. And in the end, we prove that the two connections are gauge equivalent. Okay, so this completes the proof. Okay, so I think I'm over time already. So there were a few open questions. Like for instance, we did this for unitary connections, but it would be interesting to do it for non-unitary ones. There are a few other open problems. And let me just say that, let me advertise one thing. So here are the two main references for what I've been talking about. And there's another reference, which is a book that I'm finishing, which should be published this year in the cours spécialisé de la Société mathématique de France. And the book contains more or less all the things that I've been talking about. Okay, so it was just I just wanted to advertise this book. Okay, thank you for your attention.
Thank you very much, Thibault, for the very nice talk. Thank you very much. Are there any questions or comments, please?
Well, I had a question about the simplicity in the length spectrum. So you need this for the trace formula, right? So that you could recover the Wilson loop operator. But I know that for some constant curvature arithmetic surfaces, they have like exponential growth in the length spectrum. Sorry, in the multiplicity of the length spectrum. So is there any way you think to get around that?
Yeah, to be honest, I don't know. I know that simplicity of the line spectrum is I think it's a generic condition on the metric. Yeah. There's a paper by another film called Bumpy Metrics or something. So I think it's a generic condition on the metric, but I think you're right. Like there are many examples, like algebraic examples, where the line spectrum has a lot of multiplicities, and in this case, to be honest, like no, I don't know how to do it, because basically, I mean, the problem here is that you could have constellations in the trace formula, and that's and I don't know how to.
Well, not just cancellations, right? I mean, because then you would be adding up the traces over a bunch of different orbits, and so you wouldn't know the traces of the individual ones.
Yeah, right. Yeah. But I mean, what? Yeah. No. To be honest, like I don't know how to handle this. It's a very interesting question, but I've not tried so far. So,
yeah, I guess I was going to mention one other thing is that about the multiplicities, it's not clear that from the trace you can even detect the multiplicities. So that's it's like an open question if you know the Laplace spectrum, can you detect the multiplicities in the length spectrum? And if you could, then you would show that entropy is a spectral invariant because you would have Margulis' formula. Without that, though, I mean, in negative curvature, these Morse indices are zero. So you can actually recover the length spectrum, but just not the multiplicities. So anyways, I just wanted to say that that's also a problem that appears in that context.
Yeah, thank you. Yeah.
Thank you very much. Are there any other questions or comments, please?
So the whole point is that you're trying to show that P does not depend on velocity at the
Yeah.
end, right? Could you use like the non-existence of twisted conformal killing tensor fields to make that implication?
Right. Yeah.
It sounds similar. So I was wondering why doesn't that
It is similar. So if you knew that there were no twisted conformal killing tensors, then you would be done actually in the end. So
right.
Because so you have this map P, it's invariant by the geodesic flow. I mean, it's in the kernel of bold X, and negative curvature buys you for free that it has finite Fourier content. So it means that if you go back now to the equation bold X P equals 0, the highest mode of P should be a twisted conformal killing tensor. And if you knew for some other reasons that there are no conformal killing tensors on your space, then you would be done, I think.
Right, but then the GPSU paper, do they prove the non-existent twisted conformal killing tensor fields on closed manifolds, which is your context? No?
It's on open manifolds. Yeah, on closed manifolds, it's not very clear because I mean it's obvious that there are counterexamples. It's obvious that you can build connections which do have twisted conformal killing tensors of like arbitrary degree, basically.
Oh,
But
right.
they're very they're not. I mean, typically for a generic connection, I think we actually proved it with Mihailo. For a generic connection, there are no conformal killing tensors.
Oh, I see. Okay, so in certain contexts, you might be able to use that result, but
yeah.
you.
And if you start with zero connections or something like that, then you might be able to say that to shortcut the proof here. But yeah, you would need to assume that you actually start with generic connections.
Okay, and maybe you could obtain that if, for instance, the curvature of the connection was small enough.
Right. Yeah. So that's true. If the curvature of the connection is small enough, then you can actually prove using this GPSU paper that there are no conformal killing tensors. That's right. Yeah.
Okay.
So the connections that do have conformal killing tensors have a very, very big curvature. Actually, it's like proportional to the Riemannian curvature of the space or something like that.
Yeah. Okay. Thank you.
Thank you. Any other questions, please?
Yeah, I have a quick question.
This is Rakesh. I
Sorry,
have a question. I don't have any, I mean, I'm not an expert in this area at all, but so I'm going to ask very superficial questions. So firstly, so you assume the negative curvature. So assumption. So you don't think the conjecture is true without that assumption?
So here the problem is that if you don't assume that the metric has negative curvature, you see the operator that we look at here. Are you talking about the holonomy inverse problem or the spectral inverse problem?
So holonomy one, yeah.
Okay, because for the holonomy one, the operator that we look at is the operator that to a connection you associate the trace of the holonomy of this connection along every closed geodesic. Now, if you remove and if the space has negative curvature, we know that closed geodesics are dense. They fill in, they sort of equidistribute in the space. Now, if you remove this assumption, it's not clear to me how closed geodesics will, it's like, for instance, in positive curvature, finding closed geodesics is very difficult, I think.
Okay. So I have two other questions. The second question, maybe it was already asked. So in the beginning, in the conjecture for the spectral thing, you said, it applies to closed manifolds and then manifolds with boundary. Is that correct? Is that because everything I saw seemed to be for closed manifolds? Is that am I correct?
this is only for closed. Sorry, this is only for closed manifolds.
Okay, all right. And the third thing is some more speculative. So what about the original conjecture for Riemannian manifolds? About recovering the manifold. So from whatever little I know about the plane case, so if the domain is convex, the conjecture is that it's still. So it seems so in this in the holonomy thing, your manifold is fixed.
Yes.
So you can work with the same set of geodesics, whereas in the other, when you're trying to recover the metric, so I mean, can you speculate or anything about that?
To be honest, I think that it's a very difficult question because there are, in full generality, there are counterexamples. Like, for instance, there's this paper by Vinieras where she found pairs of hyperbolic surfaces which are isospectral, but they're not isometric. But the thing is that I think that all the counterexamples that we know of have a lot of symmetries, like they have a very big group of symmetries. So I think that one could speculate that if you start with a metric which has no isometries, which has no symmetries, then maybe in some reasonable sense, the Laplace spectrum should determine the metric, something like that. It's not even clear to me how to formulate it. But,
Okay. All right. Okay. Thank you.
Thank you very much. Any other questions or comments, please?
I have a quick question. So if you think of the analog with boundary, you think that the data you're interested in is the non-abelian X-ray transform? And here you're only extracting one number, which is the trace,
yes.
which seems like a lot less information. Can you hope to, well, I guess you also have the iterates of a closed geodesic, which are in different homotopy class. And so you get the traces of the iterates.
Yes.
So is there anything, could you be greedier and say, okay, is there any more data you can claim to extract out of this and make maybe a nicer problem out of it?
Well, so the thing is that it seems like you don't have a lot of information because you only have the trace. But as you said, like you also have the trace of the iterates. So which means that in the end, what you really have is, the conjugacy class of your holonomy along every closed geodesic. Or in other words, you have it's equivalent to saying that you have the eigenvalues of your holonomy map along every closed geodesic. Now, so if I understand correctly your question, you want to do something similar in the case of surface with boundary, or of a manifold with boundary.
Yeah, or I just wonder, like, let's say, can you decide to know the whole holonomy, or is that even not a well-defined notion, like over a point, so in any of these geodesics? Or like the linear transformation that maps you back into the tau gamma G.
Right. You know that. Okay, you can. Yeah, you can.
Instead of the trace.
Right. I don't know if this would help actually. So the thing is, I mean, okay, maybe one should need to formulate the problem differently. But the problem is that we start with two connections that a priori live on two distinct vector bundles.
Oh, yeah.
And somehow we need a way to, we want to compute some data computed with respect to these connections, and we want to compare the data of these two connections even though they don't live on the same vector bundle. So if you really take the whole tau gamma, it's a linear map, but on a space on two, you get a map, linear maps on two distinct vector spaces. So it's not really clear to me like how to compare that. The only thing that I can do when I have a linear map basically is to take the trace or the determinant or actual complex numbers basically.
Yeah, that makes sense. Thank you.
Thank you very much. Are there any other questions or comments, please?
So are you recovering the bundles from the trace or all the powers of the trace? Your theorem only states the trace, I think.
Yeah. So here I didn't state the theorem, like the complete version of the theorem. What we actually consider in this theorem B is we only consider primitive closed geodesics. So we don't take, like, for a given free homotopy class, we actually don't take iterates of the same closed geodesic, but so we only take just the primitive closed geodesic. But using the hyperbolic structure of the geodesic flow, you can show that using what is called homoclinic orbits, you can actually show that if you know the trace along every closed geodesic, primitive closed geodesic, then you can actually recover the trace along any closed geodesic, like even iterates of primitive ones, which means that you start with trace along primitive closed geodesics, you end up with trace of all the iterates. So it means in the end you really get like the whole conjugacy class of your holonomy map along every closed geodesic. But that's very specific to that heavily relies on the hyperbolic structure of the geodesic flow.
Okay, interesting. Thank you.
Thank you very much. Are there any other questions or comments, please?
Hi, I also have one question. So first of all, thanks very much for the talk. This is going to be also a superficial question, but for this CAX problem, there is a version also where instead of metric, you just consider Laplace plus, let's say, potential, some lower order function. And then you ask from the spectrum, can you determine these coefficients? So it seems to me your result does provide some answer to this, right? In the case of just taking a vector bundle of rank 1, you are giving some results.
Yeah, right. So I think that in this case, it's like if you take Laplace plus potential, it's probably already known by results of Guillemin. I think that this is what Guillemin and Kazdan do in their paper. So I would say that in this case, it's already known. But it's it's true. I think that it's true that what we're doing is sort of is more or less the same thing, except that we work with vector bundles of higher rank. But what the problem you described is actually the case of like the trivial line bundle of rank 1. But I think this was already known actually by Guillemin and Kazdan and maybe other people. I don't remember.
I see. Okay, thanks.
And they also have the same assumption that the line spectrum has to be simple, because so if you start with Laplace plus potential, applying the trace formula, what you get is you recover the integral of the potential along every closed geodesic. So if you start with two potentials, Q1 and Q2, you get that along every closed geodesic, the integral of Q1 is equal to the integral of Q2. And this is a tensor tomography problem. It's like the injectivity of the X-ray transform on functions, basically. It's related to that.
I see. And do they also cover the case of like a first order terms, like a magnetic potential?
So a magnetic Laplacian is what we do actually.
I see. Okay. Great. Thanks.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? Thibault, can I ask you to go over open problems if possible? I mean, just to discuss it a little bit more. Thank you.
I need to go, but thank you, Thibault, for the talk. It was a great talk.
Thank you.
Okay, thank you very much. Are there any other questions or comments, please? If not, thank you very much, Thibault, for the very nice talk. Thank you very much, everyone, for coming. Thank you.
Thank you for the invitation.